Welcome to this video on the Carnot engine cycle and ideal efficiency. In this video, we're going to be taking a look at the most theoretical ideal engine cycle, and that is known as the Carnot engine cycle. If you haven't yet watched the reversible versus irreversible processes video, you want to check that one out first before you go on to this one so that it makes a lot more sense. So the first thing we want to do is always remember the big picture. And the big picture says that we're trying to make the most efficient engine possible. And efficiency for us in thermodynamics is defined as the most work out over the least heat input. Now if we multiply this by 100, this ratio, we get the percent efficiency of a particular engine. So we want this ratio over here to be the biggest number it can be by making the work output really, really large with the heat input as small as possible. So if we think about the reservoir models that we had talked about before, theoretically speaking, in order to have an engine do work for us, we need to have a hot reservoir and a cold reservoir. And the point of that is that we would have heat flow from one to the other, where we'd have high temperature heat, or high energy heat over here and lower energy heat over here. And on the way to that heat change, or the heat flow, work would be done as that occurred. So we're taking advantage of the fact that heat naturally flows from high temperatures to cold temperatures, and in order to get work done. Now we're going to define the work in this expression for efficiency as the difference in the high energy heat minus the exhaust heat. That would tell us how much work is done in the process, because whatever doesn't go to the low temperature reservoir is going to go to work on the way. And that is in the form of the mechanical structure known as the heat engine. So I'm going to rewrite this efficiency equation as E is equal to QH minus QC over QH. And keep in mind that I can make Qn QH because that's the input heat that's coming from the high reservoir. I'm going to split this fraction here, so I have QH over QH minus QC over QH. And what I'm left with is QH over QH, which is 1, minus QC over QH. And this model is really useful because it can tell me what the efficiency is of the engine by saying 100% efficiency minus this ratio of the exhaust heat to the input heat, and that would tell me how efficient my engine is. So let's look at how the Carnot engine cycle is defined to being the best and most efficient of all possible engine cycles. So the first thing I want to do here is on this pressure volume diagram, just explain what these dashed lines are. These are all known as isotherms, and basically all they are points on the graph where every point that falls on a particular dashed line, so on this particular dashed line, that would all be operating at the same temperature. So let's say that this is maybe the isotherm that represents 2000 Kelvin, and maybe this isotherm over here represents, I don't know, let's make it 500 Kelvin. So basically what you're saying is every pressure volume coordinate on here would use the ideal gas law to calculate the temperature. All of these have the same PV and RT ratio so that we have the same temperature. Now what Carnot said was that the best combination of processes to make a cycle would be to do the following. So what I have on here is an engine cycle, so 4 different processes that start and end at the same point. And we need to define these specifically. What we see from state A to state B, we've stayed on the same isotherm, so this is going to be considered an isothermal process, as is C to D because it stays on its own isotherm. So this is another isothermal process. But we want to distinguish the two by the fact of this arrow. This is going to be an isothermal expansion, and this is going to be an isothermal compression. Now, what's interesting here is to look at the cycle, or I'm sorry, the process from B to C, and we see that we're moving between two isotherms, which is known as an adiabatic process. So an adiabatic process, if you recall, is going to be a process in which no heat is exchanged. And we'll have another adiabatic process over here. So this adiabatic process is still an expansion. This adiabatic process is, of course, a compression. Now, in order for this very first process, A to B, to occur in isothermal expansion, we're going to have an input of heat. And so I'm going to call that one the QH value. During the adiabatic expansion, remember that there is no heat exchange, as is in the adiabatic compression, there's no heat exchange. During the isothermal compression, in order to keep the temperature the same as the gas compresses and the pressure goes up, we have to, of course, exhaust heat here, and that's going to be the QC value that's shown on the reservoir model. So you can see here that the net amount of heat exchange in this process is going to give us QH minus QC, which is what we showed as being work done. And we know that another way that we can determine the amount of work done is by calculating the area inside this. Now, if you're not in calculus yet and you don't know how to integrate over this closed shape, what's going to have to be done is an approximation, and that's totally fine. You could kind of make this, I guess, a rhombus and then calculate the amount of work done. But what we can see here that in this process is that during every single process there is work being done, because there's always going to be a volume change no matter what process you're at. Whereas what we looked at in the Otto cycle had these isochoric processes that occurred vertically, and there's no work being done in those. So all of the processes during this cycle, work is done. So we're getting the most work output here, but we're also getting the combination of that with no heat exchange during the adiabatic compression and expansion, and that's going to eliminate any excess heat loss or excess gain or excess heat needed during the process. Now, there's something very important missing from these descriptions. All of these are going to be considered reversible processes. So not only is this an isothermal expansion, it's a reversible isothermal expansion. Not only is this an adiabatic expansion, it's a reversible adiabatic expansion. And then we also need to write reversible in for all of these others. Now, this is important to note that these are reversible for the reasons that we expressed in the previous video, and that is because what we're saying here is that you need to move from A to B so slowly as you pass through all these little equilibrium positions so that no excess heat is lost during this process as you move from A to B. Another way you could look at it is saying that you would need to put more heat in if you were going to go and get the same values of A and B throughout the process. So it's really important to remember that these are reversible processes for each one that we look at. Now we know that this is going to be an ideal engine. So an idealized Carnot engine cycle is one in which all of these processes are reversible. So I could have a more realistic Carnot engine cycle by just removing the word reversible from all of these and saying that there is some sort of process going on here, but of course it's not going to be the most efficient. Now what I want you to think about is, what could I do to this cycle, keeping it the exact same processes, or the same kinds of process, but change it in such a way that I get more work output with less heat input. Pause the video and try to figure out what I could do here. Well, if you think about it, I want to get more area in this space, but I don't want to do it at too high a temperature so that I end up having a greater heat flow into the engine. So what I'm going to do here is, if I am able to actually lower this process down to this isotherm over here, so in other words, I'm going to scoot this whole process down. Basically what I'm going to have then is this additional area in addition to the yellow, and I'll have a greater input work with the same amount of input heat, which would give me the best possible scenario. And if you look at that, that means that we need to operate the engine between two greater differences in temperature. And so what you can do with an ideal Carnot engine cycle is calculate the efficiency in a very specific way, and that is to do the following. You can do 1 minus Tc over Th. This is going to allow you to calculate the efficiency between the two isotherms rather than just with the heat reference that you see in this case, or the heat ratio that you see in this case. So this only works for the Carnot engine, whereas this process over here, or this way to calculate efficiency, you can use for any engine cycle. This one only works for the Carnot cycle. And in doing this, you create the most efficient engine possible, but it's the least practical engine possible. In the next few videos, what we're going to do is take a look at entropy and start to look at how can we look at all the same things we've looked at so far, but from a slightly different perspective of entropy, and maybe more in a big picture way, why it's not possible to have 100% efficiency.